This video is going to cover another type of conic section, namely an ellipse. You're familiar with ellipses. You maybe call it an oval, but here are an example of a couple ellipses. And there's a couple interesting things to note about an ellipse, just at a kind of a first glance. They kind of come in, I'm going to call it two different structures or two different type of designs. There is what we would call on the left here a horizontal ellipse, which is wider than it is tall. And over here we have a vertical ellipse. A vertical ellipse is taller than it is wide. And you might think, just from practical standpoints or whatever, what you would see out there kind of in the real world, a good example of a horizontal ellipse would be a football. A good example of a vertical ellipse would be an egg. There's symmetry in an ellipse. There's a center to an ellipse. The symmetry is a little bit different. It looks like you have some horizontal symmetry and some vertical symmetry relative to the center. And that's true whether you have a horizontal or vertical ellipse. Now, just like a circle and all the points on the circle had a relationship with something called the center, it turns out that all the points on an ellipse also are related to some other elements inside the ellipse. And what it turns out to be is all the points on the ellipse have a relationship with a pair of points. With a circle, it was a relationship with that one single point called the center. But with an ellipse, it's a pair of points inside the shape that all the points on the outline have a common shared characteristic with. And it's as follows. I'm going to let F1 and F2 be the 2 points that I'm talking about that live inside the ellipse. And it turns out that everything in blue in here, and let me just go ahead, I'm going to do an example. Here's F1 and here's F2. And what it turns out to be, and I could do an F1, F2 over here too, but let's just work with this first one. Everything in blue I see here, if I take a point in blue and connect it to F1 and connect it to F2 and figure out how long those distances are and add those distances together, how far this point is from F1 plus how far it is from F2. When I do that for every point that's on this blue ellipse, it turns out that that combined distance is exactly the same. So that's kind of the characteristic. If you go to Desmos and just pull this up, I have it on the portal, you could go look, you'll see that demonstration. It's an interactive ellipse and you can see that. You'll have a kind of a move around the ellipse and you'll notice they have a couple segments connected from every point that you travel on to F1 and F2. And you'll notice that the combined distances will always be the same. So that's kind of a general structure of an ellipse, how you build one. Let's talk about the characteristics. An ellipse always does have a defined center. And it's going to have what I talked about before. There's going to be horizontal and vertical symmetry relative to that center. And those lines that go through the center are called axes. You'll have a horizontal axis, you will have a vertical axis. They go through the center. So an ellipse's vertical axis runs from the bottom to the top through the center. The horizontal axis runs from left to right or right to left, whichever way you want to say. And it also runs through the center, from far left to far right, through the center. Now, it turns out, and you can see in both of our examples, that one of the axes, either the horizontal or the vertical, in this case the horizontal axis, in this case the vertical axis, is longer than the other axis. And so what we always find out is the longer of the two axes is called the major axis. The shorter is called the minor axis. And so if you put that together, it leads us into a vertical ellipse will have a vertical major axis. That's the longer axis. A horizontal ellipse will have what? A longer horizontal axis. Major axis will be horizontal in a horizontal ellipse. The major axis will be vertical in a vertical ellipse. And then obviously the minor axis is the shorter of the two. The two tips of a major axis are called vertices. The two tips of a major axis. So over here, there are my two vertices I've marked here and here. In my vertical major axis ellipse, those 2 points are the vertices. The endpoints are the pieces that are at the top and bottom or right and left of the minor axis. So if I go a little x right here and an x right there, those are the endpoints of what? The minor axis in this horizontal ellipse. And over here, if I went x and x, those are my endpoints of this vertical major axis ellipse. So vertices are always at the tips of the major axis. Endpoints are at the tips of the minor axis. Now, there's a couple more things that you're going to see. The distance from the ellipse's center to either of the vertexes is going to be given the value a. And the distance from the ellipse's center to either endpoint is going to be given the value b. Those 2 points we talked about, and you'll see this on the next page in a second, but the 2 that I put up here, the F1 and the F2, they are called the foci, F-O, plural of focus, foci of the ellipse, those 2 points. And it turns out that the distance that these 2 foci are, F1 and F2 are from the center, is the exact same amount. By the way, these 2 points, they live on the major axis of the ellipse. And you're going to find out that the distance from the center to either of those 2 points, F1 or F2, is going to be given the value of c. The center of the ellipse serves as the midpoint of the segment that connects the 2 foci. So there's a lot of stuff here. We'll come back. You're going to see it as we work through some of these graphs. No sweat there, just we will see it. Unlike the circle where we derive the equation, I'm going to provide the equation to you, the standard equation of an ellipse that's centered at hk. And you're going to notice some similarities. Look, hey, you got an x minus h squared. You got a y minus k squared. Same type of structure when you're centered with a circle at h and k. But what's different? Well, there's a couple pieces. Your x minus h squared is going to be divided by a squared, or y minus k divided by a squared. We'll explain that in a moment. And your other piece, the other element that you're going to have, is going to have a b squared over it. And it turns out, if you have a horizontal ellipse, we're going to assign the value of a as the length of the major axis. And that's true in both cases. A vertical ellipse has a vertical major axis that goes up and down. And so the value of a is always going to trail and go with the coordinate that's associated with the major axis. Horizontal ellipse, put your value of a with your x coordinate. Vertical ellipse, you're going to go ahead and put your a with the y coordinate. So always remember, a is going to map, and a squared here is how we're going to get an equation, but a will always map to the major axis, the length of that. So one other piece, remember how we always had in the circle equation was equal to r squared? Well, in an ellipse, you're going to do something a little bit different, and you're going to set it. The equation actually will set you equal to 1. So this is the equation. I'm going to kind of keep this tucked off to the side for a moment, and we're going to go ahead and work through a visual. Let me see if I can put this all in. Yeah, we got some viewing mode here that you can see all the different pieces. Here is a horizontal ellipse. And here's what I'd like you to notice about it. Here's our equation, hk. And what do we notice? This is a horizontal major axis. What's the length? Well, if you go from hk and you travel an amount of a, you're now going to be at the new point h plus a comma k. And you go to the left, h minus a, k. That's the point over here. A units to the right, a units to the left. And for our minor axis, which in this case is vertical, we say it's the value of b. You go up b from hk, and you wind up at the point h comma k plus b. And you go down b units from hk from the center, and you'll wind up at the point h comma k minus b. Here are your 2 vertexes, Horizontal, because our major axis is horizontal. Here are your endpoints, because our minor axis is vertical. And then the last piece, notice, HK, H plus C, comma K, we've moved what? C units to the right. This is our first focal point, foci. And the second one is what? C units to the left. H minus C, comma K. What's happened? Our K value has stayed the same. Our Y coordinate stays the same on all these pieces. And all we did is what? We shifted C units to the right. C units to the left. H minus C. We've shifted C units to the right. H plus C. So I just want you to see all those different pieces here. And we could do the exact same thing here if we wanted to on a vertical ellipse. We'll hold off on that for a couple seconds, but let's talk about the process of graphing an ellipse. We'll do one more thing just while we're here. One other addition. How big is the major axis? Well, what do you know? You say to get to one vertex, you go A units to the right, or to get to the other, you go A units to the left. How long is this total distance? Well, it's A plus A, or 2A. So the overall length of the major axis is equal to 2 times the value of A. The length of the minor axis is nothing more than 2 times the value of B. So, how do you graph an ellipse? First things first, use the standard form of the equation to identify the center. That's going to be at H and K. Next, identify the A and B values from the equation to determine whether you have a vertical or horizontal major axis. An important point. A is always going to be greater than, or let's do equal to B. We'll explain that in just a little bit down the road. But your major axis always has to be bigger than, or no, it cannot be less than your minor axis. Once you know whether you have a major axis, let's say you have a horizontal major axis, then from the center go left and right by the amount A to mark the vertices. If you have a vertical major axis, all you need to do is go up A units and go down A units from the center to get your vertex. You can do the same thing with your minor axis, except what do? You move B units. If you have a vertical minor axis, you're going to go up from the center B units, down from the center by B units. If you have a horizontal minor axis, go to the center, move yourself B units to the left, move yourself B units to the right, and you're in good shape and you got those 2 endpoints done. And from there, just go ahead and sketch. You got a center, you kind of have the 4, I like to call it the poles of your ellipse, and you can go ahead and draw. So we're going to practice that. There's one more thing to just tuck away. Notice, and this is a formula that you'll be given, the value of C, how far your foci are from the center, is given by the following equation. C is equal to the square root of A squared minus B squared. So we're going to work that through with a couple examples on the next page. You have an equation, and you're going to go ahead and build the ellipse that is represented by this equation. X squared over 4 plus y squared over 36 equals 1. You notice what? You don't have an x minus or a y minus or an x plus y plus something squared. That's telling you that the center is at 0, 0. I'm going to go ahead and just mark my center. It's not part of the ellipse, but I'm going to use it for the sake of drawing. Now, looking at our 2 different types of equations, you want to compare your A and your B values, your A squared and your B squared values. Remember, the bigger one in the equation is always going to be A squared. A squared equals 36. B squared equals 4. So that means A must equal 6, B must equal 2. Square roots. My A goes with my y coordinate. I must have a vertical ellipse. It's going to be what? Taller than it is wide. Okay, here's my value of A. Vertical major axis. I'm going to do up and down by the amount A. I'm going to go up 6. 1, 2, 3, 4, 5, 6. I'm going to go down 6 from the center. 1, 2, 3, 4, 5, 6. Now, what do I know about B? It's equal to 2. I'm going to move left and right from the center by 2. 1, 2. 1, 2. And what can I now do? I got my 2 vertices. I got my 2 endpoints. I'll go ahead and try to draw an elliptical shape. Sure looks pretty much taller than it is wide. So I like what I have here. Now, let's identify a couple other features. The center is at 0, 0. The vertices, well, major axis owns the vertices. Hey, this point is 0, 6. This point is 0, -6. Identify the endpoints. 2, 0. -2, 0. And then the last piece, they asked me, hey, can I identify the foci? Well, number one, the foci are going to live somewhere on the vertical major axis. And we were given the equation that C equals A squared minus B squared, the square root of that. C equals the square root of 36 minus 4 equals the square root of 32. Now, if we go to our calculator real quick, square root of 32, I'm going to need to estimate this. 32, take it to the 0.5 power, is equal to 5.66 or so. So what's that telling me? The foci is located 5.66 units away from the center along the major axis. So if I go up, it actually gets pretty doggone close to the tip. But in any case, I'll just go ahead and kind of mark those 2 points. They'd be at what? My foci would be at 0, 5.66, and 0, -5.66. And so there are all the pieces in place. Let's do one more just for practice, and then I'll have you turn loose and work through the last problem. Our middle one, x squared over 49, y minus 1 squared over 36. Where's my center? At 0, 1. There's my center. Now, what do I have? 49 is a squared. 49 is bigger than 36. A squared equals 49. A equals 7. B squared equals 36. B equals 6. What do I now know? I have a horizontal major axis on this ellipse. Let's go ahead and find my vertices. I'm going to go what? 7 to the left. 1, 2, 3, 4, 5, 6, 7. I'm going to go 7 to the right. 1, 2, 3, 4, 5, 6, 7. I'm going to go what? 6 up. 1, 2, 3, 4, 5, 6. I'm going to live right at the top of my graph. I'm going to go 6 down. 1, 2, 3, 4, 5, 6. Can I draw? Absolutely. And you'll notice that A and B's are pretty close to each other, so this thing, and I'm not going to do the best job of it, but it's starting to look a little bit more like a circle, but it is still a horizontal major axis. My endpoints of the, excuse me, let's go ahead. Center, already handled that. My vertices are going to live what? Left and right, because this is a horizontal ellipse. This point is -7, 1. This point is 7, 1. Up here, I'm at 0, 7, 6 units up from the center at 0, 1. Down here, 6 units below the center, 0, -5. So I've identified my 2 vertices. I've identified my 2 endpoints. I'm asked to identify my foci. Well, here we go again. C equals the square root of 49 minus 36 equals the square root of 13. If I go to my calculator real quick, 13, take it to the 0.5 power, and I get 3.6. So what's that tell me to do? C is equal to 3.6. The foci live along what? The horizontal axis. It lives along the major axis, and this is a horizontal ellipse. Move over 3.6. 1, 2, 3, and about a half. Move over 1, 2, 3, and a half. And now I've identified my two foci. By the way, where do they live at? 3.6, comma 1, negative 3.6, comma 1. Last problem, we'll talk our way through it real quick. I'll let you work it and draw it. It looks like it's a vertical major axis because 25 is bigger than 9. A squared is going to be 25. B squared is going to be 9. A is 5. B is 3. Where am I centered? 4, negative 3. And I'll let you work yourself through the rest of this. Now, sometimes you're going to be asked to convert two ellipse equations into standard form. And the important thing when you look at this is to notice the following. You always want your right-hand side to be equal to 1 if you're going to create an ellipse equation. So when I have 16x squared plus 9y squared equals 144, well, I'm going to divide everywhere. 16 over 144, 16x squared over 144, plus 9y squared over 144 equals 144 over 144, or 1. Now, what's interesting is if you go to your calculator, or if you just kind of realize something, 16 times 9 is actually equal to 144. This becomes, then 16 over 144 is actually 1/9. X squared over 9 plus, well, 9 over 144 must be 1 over 16. Y squared over 16 equals 1. I've now converted this ellipse into standard form. Over here, a couple pieces of work to do. X minus 1 squared plus y plus 4 squared equals 49. And by the way, when you stare at that, I hope what you realize is, gee whiz, this looks like the equation of a circle. R squared. Hey, the square root of 49 happens to be 7. This looks like it's a circle with what? A center at 1, negative 4, and a radius of 7. But let's just go ahead and take it into ellipse form, just kind of following what we've already done. X minus 1 squared over 49 plus y plus 4 squared over 49 again equals 1. What's interesting here? A squared and b squared are equal to each other. And what you'll find out is when you see something like that, when you have a squared and b squared equal to the same value, a and b must be the same value. And that's also telling you that your major axis and minor axis must be the same length. And whenever that happens, it turns out that you have not only an ellipse, but a special type of ellipse that actually is a circle. So a circle, if you think about it, truly qualifies as an ellipse in which the major and minor axis are identical, are the same. So you might see this in circular form. That's a perfect example. X minus h squared plus y minus k squared is equal to r squared. But bottom line, you're really solid here, and you can also define this as an ellipse that has the same major axis in both in terms of its size, same major axis in both sides. So this is our work with ellipses and circles. Focus here on ellipses. There's a lot of work to do here, but if you get this general structure and understand the process of how to draw one, it's going to be very easy for you to work with these types of conics.